Now that we've gone through all of the steps in a z-hypothesis test for a population mean, let's go through another example in entirety. Let's say that a researcher is interested in examining the potential effect of heavy maternal alcohol consumption while pregnant on a child's IQ score. The researcher has found that previous studies have shown that heavy alcohol consumption during pregnancy may affect IQ scores in children. The researcher knows that the average IQ score for the general population is 100, with a standard deviation of 15. The researcher then takes a random sample of 100 children whose mothers reported heavy consumption of alcohol while pregnant. These children are given an IQ test, and the researcher finds the mean IQ in this group of children was 96. The researcher is wondering, do results from this study provide evidence that alcohol consumption during pregnancy has an effect on child's IQ scores? So let's go through each of the steps in conducting our hypothesis test. The first step is defining our research question or problem of interest. In this case, our research question would be, does the mean IQ score of children whose mothers reported heavy alcohol consumption while pregnant differ from the average IQ score in the general population of 100? Our next step is formulating hypotheses. Since we are testing to see if the average IQ score of the population from which our sample came of children whose mothers reported heavy alcohol consumption while pregnant differs from the average IQ score of the general population of 100, our null hypothesis would be mu is equal to 100, asserting that there is no difference, and our alternative would be mu is not equal to 100, asserting that there is a difference. Our next step will be determining a decision rule. In this case, I'm going to test using the standard alpha level of 0.05. The fourth step is calculating the test statistic, recalling that the formula for the z-statistic is x bar, or the sample mean, minus mu, or the hypothesized population mean, divided by sigma, or the population standard deviation, over the square root of n, or the sample size. In our case, x bar is 96, mu is 100, sigma is 15, and our sample size is 100. This would give us -4 divided by 15 over 10, which would give us -4 over 1.5, which would give us finally our z-statistic of 2.67 rounded to the hundredths place. We can also find the p-value associated with our calculated statistic by looking at our standard normal table to find the value associated with the z-statistic of 2.67. This will get us a p-value associated with our two-tailed hypothesis test statistic of 0.0076. Our next step is to make a decision about the null hypothesis. We can make a decision about the null by comparing our p-value to our chosen alpha level. For our example, our alpha level was 0.05. Since our p-value of 0.0076 is less than 0.05, we will reject the null hypothesis. This would indicate that results of the test are statistically significant. Our final step is interpreting our decision. We have rejected our null hypothesis, so we are saying that we have enough evidence to conclude that the population of children whose mothers report heavy alcohol consumption while pregnant do not appear to have the same average IQ score as the general population. We have only tested whether or not it was equal, so it would not be appropriate to conclude it was higher or lower in this case. We would just conclude that it does not appear equal. If we did want to make a claim about a certain direction, whether higher or lower than a comparison value, we can change the type of z-test that we are conducting. If we were only interested in testing whether or not it differed in a single direction, we can use what's called a one-tailed test. A one-tailed test would follow similar procedures as we've discussed, but you would have a slightly different null and alternative hypothesis and a different critical region for rejecting the null. Let's look at an example of both two-tailed tests and one-tailed tests for comparison. In a two-tailed test, the null hypothesis is that mu is equal to some value of interest, and the alternative is that mu does not equal that value. If our alpha level, for example, was 0.05, we would want to split that alpha in two, which would give us 0.025 in both tails, representing the critical regions in the two tails where we will reject the null if our test statistic falls within. If we want to look in only one direction, say for example, if our research question of interest is does our population of interest have a lower mean than our comparison population, we would want to do a one-tailed test. You can do a one-tailed test in either direction depending on your research question of interest. Remember that your alternative hypothesis is often what you are a bit more interested in your research question, so if you were interested in assessing whether your population of interest has a lower mean than a comparison population, you would want your alternative hypothesis to be mu is less than that comparison value for the population mean. And the null that you are actually testing would be the opposite of that, or greater than or equal to that comparison value, indicating that nothing special is going on with your population of interest, or that it is not less than your comparison value. In this example, you are only interested in rejecting the null when it falls below a certain point. So your rejection region, for example, corresponding with an alpha level of 0.05, would all be in one tail of the distribution, specifically the lower tail of the distribution. Similarly, in a test where our research question of interest is does our population of interest have a higher mean than some comparison population, we would want to do a one-tailed test in the opposite direction, with an upper-tailed critical region. Our alternative hypothesis would be that mu is greater than the comparison population mean, and our null that you are actually testing would be that mu is less than or equal to that same value. Your rejection region, for example, corresponding with an alpha level of 0.05, would all be in the upper tail of your distribution.